In the early 1960s, American railroads operated under a seemingly simple philosophy. If 3,000 horsepower could move a freight train, then 5,000 horsepower had to be better. It was an era of raw optimism in diesel technology, where the solution to every operational challenge appeared to be cramming more power into fewer units. General Electric's answer to this demand was the U50, a locomotive that pushed boundaries in ways the company hadn't fully anticipated. With two 16-cylinder diesel engines producing a combined 5,000 horsepower, it was the most powerful single-unit diesel locomotive in the world when it entered service in 1963. But the U50 quickly exposed a fundamental problem that would reshape how the railroad industry thought about motive power. Horsepower means nothing if you can't transfer it to the rails. The U50 wasn't a failure in the conventional sense. It was a learning experience, one that cost millions of dollars and taught the industry that adhesion, control, and weight distribution mattered far more than raw engine output. This is the story of how ambition outpaced engineering and how one locomotive helped define the limits of what was possible with the technology of its time. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. To understand why GE built the U50, you need to understand the operational pressures railroads faced in the early 1960s. Freight traffic was growing, but profit margins weren't. Railroads were locked in brutal competition with trucking companies, and labor costs were climbing. The solution, as management saw it, was to move more tonnage with fewer locomotives and fewer crew members. Train weights had exploded over the previous decade. What had been a 4,000-ton freight consist in the early 1950s was now pushing 6,000 or even 8,000 tons on Western main lines. Cars were heavier, loads were denser, and consists were longer. Railroads wanted to eliminate helper locomotives on grades and reduce the number of units needed per train. The math seemed straightforward. One 5,000 horsepower locomotive could replace two 2,500 horsepower units, cutting acquisition costs, maintenance expenses, and fuel consumption. But there was another factor driving this thinking. Multiple unit control wasn't as reliable as railroads wanted. While MU connections allowed locomotives to work together, synchronization issues still plagued consists. Throttle response varied between units. Braking wasn't always coordinated, and electrical failures could leave one unit idling while others carried the load. A single, massively powerful locomotive eliminated those problems entirely, or so the theory went. For General Electric, the U50 represented more than just a technical challenge. It was a strategic gamble. GE had only entered the road diesel market in 1960 with the U25B, and they were still the underdog fighting for market share against EMD's dominance. EMD had decades of refinement in locomotive design, a vast service network, and the trust of nearly every major railroad in North America. GE needed something dramatic, a headline locomotive that would prove they could not only compete with EMD, but surpass them in raw capability. Western railroads were particularly interested. The Union Pacific, Southern Pacific, and others operated across mountain ranges and deserts where sustained power over long distances mattered more than quick acceleration. These were territories with relatively straight track, long tangent sections, and grades that punished underpowered locomotives. If any environment could use 5,000 horsepower effectively, it was the American West. The engineering challenge GE faced was straightforward but daunting. No single diesel engine in production could reliably produce 5,000 horsepower. EMD's 16-cylinder 645 engine topped out around 3,000 horsepower, and GE's own FDL-16 was rated at 2,500 horsepower in the U25B. Developing an entirely new, larger engine would take years and cost tens of millions in development, money GE couldn't afford to spend as a newcomer to the locomotive market. So, GE chose a different approach. Put two engines in one locomotive. The U50 would essentially be two U25B power plants installed on a single, extended underframe. Each FDL-16 engine would drive its own main generator, and each generator would power 4 traction motors. The concept wasn't entirely unprecedented. Steam locomotive designs had occasionally used multiple boilers or engines, but it was radical for a diesel. The physical result was a locomotive 83 feet long, riding on 4 two-axle trucks. It looked like someone had taken 2 road switchers and welded them together. The truck configuration was designated B plus B, B plus B, 2 sets of twin-axle trucks with a span between them. Each truck set supported 1 engine, 1 main generator, and 2 traction motors per truck. In theory, this distributed the locomotive's 557,000-pound weight across 8 axles, giving it excellent adhesion characteristics. Each axle carried roughly 69,000 pounds, well within the limits for mainline track. But GE's engineers underestimated the complexity this arrangement introduced. The trucks weren't independent. They were part of a single rigid frame. This meant the locomotive's behavior during acceleration wasn't simply the sum of 2 U50's working together. The trucks interacted dynamically, loading and unloading based on grade, curvature, and how the frame flexed under stress. In perfectly flat straight track conditions, weight distribution might be ideal. But introduce a curve, a grade transition, or uneven rail, and suddenly some axles were carrying significantly more weight than others. This mattered because adhesion, the ability of a wheel to grip the rail without slipping, is directly proportional to the weight pressing down on that wheel. If one axle was carrying 75,000 pounds, while another was down to 60,000 pounds due to frame flex, their adhesion characteristics were completely different. Apply the same electrical current to both traction motors, and the lightly loaded axle would break loose while the heavily loaded one was still gripping. GE's gamble was that raw power would overcome these complications. The locomotive had 5,000 horsepower available, far more than any conceivable adhesion limit in normal conditions. Even if it wasted some of that power to wheel slip, plenty would remain to move the train. What GE didn't fully account for was how wheel slip would cascade, how control systems would struggle to respond, and how crews would react when the locomotive didn't behave predictably. The U50's technical systems reveal why it struggled in service. At its core, the locomotive used technology that was already mature by 1963 standards: DC, traction motors, electrical load control, and mechanical truck designs that trace their lineage back to the 1940s. The problem wasn't that any individual component was flawed. The problem was that these components, when asked to manage 5,000 horsepower across 8 axles on a long, rigid frame, operated at the edge of their capabilities. Each of the 8 axles was powered by a DC traction motor. These motors received electrical current from the 2 main generators, with voltage and amperage controlled by the locomotive's load regulator. The load regulator was essentially an electromechanical computer that monitored generator output and adjusted field excitation to prevent overloading the engines. But the system had no individual axle control. Current was distributed in parallel to groups of motors, not precisely metered to each axle based on real-time adhesion conditions. Wheel slip detection in 1963 was primitive by modern standards. The system relied on rate of change sensing. If an axle's rotational speed increased too quickly relative to the locomotive's actual speed, the system interpreted this as wheel slip. But this detection happened after the slip had already begun, and the response was equally crude. The load regulator would reduce power across all motors simultaneously, often by a significant margin, which caused a sudden drop in tractive effort and a lurch that crews could feel in the cab. The truck design itself introduced additional complications. The U50's wheelbase, the distance between the first and last axle, was nearly 70 feet. This created leverage effects that weren't present in shorter locomotives. When the U50 entered a curve, the outer trucks experienced different forces than the inner trucks. The frame wanted to travel in a straight line, but the rails forced it into an arc. This created binding and unequal loading across the trucks. The leading truck in a curve might be pushed outward, unloading some weight from its inner wheels, while the trailing truck was pulled inward, creating different adhesion characteristics. Grade transitions, the points where level track meets an incline, or where an upgrade transitions to a downgrade, were particularly problematic. As the locomotive's nose lifted onto a grade, weight shifted rearward. The rear trucks momentarily gained adhesion while the front trucks lost it. If the engineer was pulling hard at the moment of transition, the front trucks could break loose. The control system would sense this and cut power, but by the time the correction took effect, the rear trucks were fully loaded and could have used more power. The result was a seesaw effect, where the locomotive never fully utilized its available adhesion. Weight distribution varied more than GE anticipated. While the nominal weight per axle was around 69,000 pounds, actual loading fluctuated based on fuel levels, water for cooling, and how equipment was positioned within the locomotive. More critically, the suspension system, designed to keep wheels in contact with the rail over uneven track, had limited travel. On jointed rail, which was still common in the 1960s, the wheels were constantly encountering small vertical displacements as they rolled over rail joints. A wheel momentarily lifted even a quarter-inch lost almost all its adhesion. At 5,000 horsepower, that momentary loss was enough to initiate slip. The control systems of the era simply couldn't respond fast enough. Modern locomotives use microprocessor control with response times measured in milliseconds. The U50's electromechanical controls operated on timescales of tenths of a second, fast enough for moderate power levels, but inadequate for 5,000 horsepower distributed across a frame with complex loading dynamics. By the time the system detected slip, reduced power, and waited for the wheels to regain traction, the locomotive had often wasted several seconds and hundreds of feet of forward progress. This is why the U50's 5,000 horsepower was often theoretical rather than practical. Crews learned to operate the locomotive at reduced throttle settings, typically running at the equivalent of 4,000 to 4,500 horsepower, because pushing to full power invited wheel slip that the locomotive couldn't manage. In effect, the U50 became an expensive, mechanically complex locomotive that performed like a well-controlled 4,000 horsepower unit. The U50's wheel slip problem wasn't constant, it was situational, which made it more frustrating for crews. Under ideal conditions, the locomotive performed adequately. On dry rail, on flat or gently graded track, with a train already in motion, the U50 could sustain 5,000 horsepower and move staggering tonnage. But these ideal conditions were the exception, not the rule. Starting a heavy train from a standstill was where the U50 struggled most. This is when tractive effort demands are highest, and when the margin between adhesion and slip is narrowest. A locomotive starting a 6,000-ton train needs to overcome static friction in every wheel, bearing, every coupler, and every point where steel meets steel. This requires maximum torque from the traction motors, which means maximum current and maximum force trying to rotate the wheels. If the track is perfectly dry and clean, adhesion might support 25% of the locomotive's weight as tractive effort. For the U50, that's roughly 140,000 pounds. But introduce any contaminant, morning dew, leaf residue, light rain, diesel fuel spilled during refueling, and adhesion drops to 15% or even 10%. Suddenly, the U50 had more power than it could use. The physics of adhesion are unforgiving. The coefficient of friction between a steel wheel and a steel rail is already low compared to rubber on pavement, around 0.25 to 0.30 in ideal conditions. This is why trains can't climb steep grades the way trucks can, and why they require such long stopping distances. Any reduction in this coefficient, even slight, dramatically affects performance. Rail that's been polished smooth by passing traffic, rail that's coated with a microscopic layer of oxide, rail that's wet from humidity, all of these reduce the available adhesion. When a wheel begins to slip, it creates a feedback loop. The instant a wheel loses grip, it accelerates. This generates heat at the rail contact point, which can actually reduce adhesion further by temporarily softening the rail surface or vaporizing any moisture present. The spinning wheel also polishes the railhead, making it even slicker for the next wheel that passes. If multiple axles slip simultaneously, which they often did on the U50, because current was distributed in groups, the locomotive could come to a near standstill while the wheels spun uselessly. The control system's response made things worse. When slip was detected, power was cut across all motors. This was necessary to stop the slip, but it meant the locomotive lost all forward momentum. The engineer had to wait for the wheels to resynchronize with actual speed, then gradually reapply power, but starting from a lower speed meant even higher tractive effort demands, making another slip event likely. Skilled engineers learned to feather the throttle, applying power in pulses rather than steadily, to keep the wheels on the edge of slipping without crossing into full slip. This worked, but it required constant attention and reduced the effective horsepower significantly. Curves introduced lateral forces that complicated adhesion further. As the U50 entered a curve, centrifugal force pushed the locomotive outward against the outer rail. This altered the normal force between wheel and rail in complex ways. The outer wheels experienced increased lateral force, which geometrically reduced their available longitudinal adhesion. The inner wheels might lift slightly due to the frame's rigidity. The result was that adhesion available for forward motion dropped even though the locomotive's weight hadn't changed. Crews learned to reduce throttle before curves, costing time and momentum. Grades combined with curves created the worst scenarios. Western main lines frequently featured long curves on ascending grades, exactly where railroads wanted maximum power. The U50 would enter such a curve pulling hard, and within seconds, slip would begin. The engineer would reduce power, losing speed, which meant the train would require even more power to keep moving. In some cases, trains stalled on grades because the U50 couldn't deliver sustained power without slipping. Track and wheel damage accumulated over time. Wheel slip generates intense localized heat, enough to temporarily melt the rail surface and create flat spots on locomotive wheels. Repeated slipping wore wheels unevenly, requiring more frequent wheel truing in the shop. Railheads developed slip marks, burnished, hardened areas where wheels had spun repeatedly. These hardened spots actually made future adhesion worse, creating a vicious cycle. Maintenance departments reported increased costs for both wheel and rail replacement on territories where U50s operated regularly. The frustration for crews was that the locomotive's power was there. They could hear both engines roaring, could see the load meter showing massive current flow, but that power wasn't translating into forward motion. It was being wasted as heat, noise, and mechanical stress. Experienced engineers developed techniques to work around the problem, learning the track conditions and specific locations where a slip was most likely, adjusting their throttle work accordingly. But this meant the U50 required skilled operators to achieve even moderately acceptable performance, whereas a well-designed locomotive should perform reliably regardless of operator experience. The U50 entered service with Union Pacific and Southern Pacific beginning in 1963. Union Pacific rostered 23 units, while Southern Pacific purchased 3. The railroads had high expectations. These locomotives represented significant capital investment, and they were supposed to revolutionize freight operations on mountain grades and long desert crossings. In specific operating conditions, the U50 met expectations. On long, straight runs across Nebraska or Wyoming, where the track was relatively level and trains were already up to speed, the U50 could sustain 60 or 70 miles per hour with 100-car consists. The locomotives excelled in sustained speed applications where starting and acceleration weren't frequent. Running at track speed on gentle grades, the U50 could outperform multiple smaller units simply because it didn't have the parasitic losses of multiple engines idling or the weight penalty of additional locomotive frames. But these ideal conditions represented a minority of the locomotive's service life. Most freight operations involved frequent starts and stops, varying grades, and track conditions that change with weather and season. The U50s were assigned to mainline freight and helper service in mountainous territories. It's exactly where their wheel slip problems were most pronounced. Mountain starting was a recurring nightmare. Sherman Hill on the Union Pacific, the Wasatch Range, the Sierra Nevada crossings. These were places where heavy trains often stopped for meets, crew changes, or traffic delays. When a U50 had to restart a 6,000-ton train on a 1.5% grade, the wheel slip problems became operationally crippling. Engineers would spend minutes carefully balancing throttle and sanders, sometimes failing multiple times before getting the train moving. Helper locomotives were often needed, negating the entire point of having a 5,000 horsepower unit. Curved track was equally problematic. Western railroads had invested in relatively straight routes, but curves were unavoidable in mountain territories. The U50's long wheelbase and rigid frame made it handle poorly in curves compared to shorter locomotives. The binding and unequal loading issues meant that even moderate curves triggered wheel slip if the engineer was pulling hard. Crews learned to reduce power before curves, but this meant losing momentum precisely where they needed it most, on ascending grades through mountain passes. Yard and terminal operations revealed another set of problems. The U50 was simply too large and powerful for switching or positioning cuts of cars. Its minimum continuous speed was too high for precise coupling, and its massive tractive effort could easily break couplers or damage draft gear if applied carelessly. Railroads found themselves unable to use the U50 flexibly. It was a mainline-only locomotive, unsuitable for the varied tasks that road freight units typically handled. Maintenance complexity exceeded expectations. 2 engines meant twice the fuel system maintenance, twice the cooling system servicing, and twice the points of failure. When one engine developed problems, the locomotive's output dropped by half, but it still required a full shop visit to repair. The extended frame required specialized lifting equipment. Parts inventory doubled. Maintenance crews had to track twice as many oil changes, filter replacements, and inspection intervals. The U50's availability rate, the percentage of time it was ready for service rather than in the shop, was noticeably lower than conventional single-engine units. Cooling system problems plagued the U50 throughout its career. 2 engines generating 5,000 horsepower produced enormous amounts of waste heat. The radiator sections and cooling fans had to dissipate this heat, and in desert environments or during sustained mountain climbing, the cooling system struggled. High coolant temperatures would trigger automatic power reductions, and in extreme cases, engine shutdowns. Crews reported that U50s frequently overheated on long grades in summer, requiring them to stop and let temperatures drop before continuing. Fuel consumption was higher than anticipated, while the U50 used less fuel than 2 separate locomotives under ideal conditions. Its real-world fuel efficiency was poor. The constant wheel slip events wasted fuel, and the need to run both engines even when full power wasn't required meant the locomotive rarely operated at its most efficient point. Railroads calculated that the fuel savings versus multiple smaller units were minimal and sometimes negative. By the late 1960s, railroad conclusions about the U50 were clear. The locomotive had demonstrated that raw horsepower wasn't the limiting factor in freight operations. Adhesion and control were. A well-designed 3,600 horsepower 6-axle locomotive with proper weight distribution and responsive wheel slip control could outperform the U50 in most practical situations. It would be more reliable, easier to maintain, more flexible in assignment, and cheaper to operate. The U50's complexity and specialized nature made it economically unviable. Union Pacific withdrew the last U50s from service by 1974, barely a decade after they were built. The locomotives had never fulfilled their promise, and the railroad industry moved on to designs that prioritized control and reliability over raw power output. The U50's significance lies not in what it achieved, but in what it taught. The locomotive forced the railroad industry to confront fundamental truths about motive power, lessons that shaped diesel locomotive development for the next 30 years. The primary lesson was that horsepower without adhesion is meaningless. A locomotive can have 10,000 horsepower available, but if it can only apply 3,000 horsepower to the rails before the wheels slip, the extra power is nothing more than expensive, complex machinery. This shifted engineering priorities away from brute force and towards sophisticated control. Adhesion management became as important as power output. The U50 demonstrated that control systems were critical. The electromechanical wheel slip detection and correction systems of the early 1960s simply couldn't manage the power levels that contemporary engines could produce. This drove development of electronic control systems throughout the late 1960s and 1970s. GE's later -7 series, introduced in 1976, featured improved solid-state controls that could respond faster and more precisely to wheel slip. These controls didn't prevent slip entirely, but they managed it well enough that locomotives could operate closer to their adhesion limits without the catastrophic slip events that plagued the U50. The experience also validated the 6-axle locomotive concept. Instead of trying to concentrate maximum power in a 4-axle arrangement with twin engines, the industry moved towards 6-axle designs with better weight distribution. A 6-axle locomotive like EMD's SD40 or GE's U30C distributed weight more evenly, had more adhesion available simply because more wheels were pressing on the rail, and handled curves and grade transitions more predictably. The 6-axle truck arrangement became standard for high horsepower. Road freight locomotives, a configuration that persists today. GE incorporated lessons from the U50 into their subsequent designs. The company's engineers realized that locomotive performance depended on the entire system: frame design, truck geometry, suspension characteristics, motor control, and wheel slip management all had to work together. The U30C, introduced in 1967, was a far more refined design that produced 3,000 horsepower from a single engine with excellent reliability. GE's later Dash 8 and Dash 9 series built on this foundation, incorporating microprocessor control and advanced adhesion management. The U50's legacy extended even further into the development of AC traction. The fundamental problem the U50 faced, controlling power delivery to maintain adhesion, was eventually solved not by better DC motor controls, but by switching to AC traction motors with individual axle control. AC traction technology, which became commercially viable in the 1990s, allows each motor to be controlled independently based on real-time adhesion conditions. Modern AC locomotives can apply nearly their full horsepower continuously because the control system actively prevents wheel slip on each axle individually. This technology traces a direct lineage back to the problems the U50 exposed. The U50 also taught railroads to be skeptical of radical designs. The twin-engine, super locomotive concept seemed logical on paper, but it introduced complexities that couldn't be solved with 1960s technology. Railroads became more conservative, favoring proven, incremental improvements over dramatic leaps. This conservatism shaped the industry's approach to innovation. New technologies had to demonstrate clear, measurable advantages in real-world service, not just impressive specifications. Perhaps most importantly, the U50 demonstrated that operational flexibility matters more than peak capability. A locomotive that excels in one specific condition but struggles in others is less valuable than a locomotive that performs consistently well across varied situations. Modern locomotive designs prioritize versatility, reliability, and ease of maintenance alongside raw power. The U50's narrow operating envelope, the limited conditions where it performed well, made it unsuitable for the varied demands of railroad operations. The U50 didn't fail because it was too powerful. It failed because the technology to harness and control that power didn't exist yet. The locomotive was a glimpse into the future, a future where 5,000 horsepower or more could be routinely managed and applied effectively. But in 1963, that future was still decades away. The U50 served as an expensive, tangible reminder that engineering ambition must be matched by technical capability, and that sometimes the most important breakthroughs come from learning what doesn't work.